All right, so we have 11.4 part 2 here, which is compare values using z-scores. Oh, bummer. I thought I had something saved to the clipboard here. Let me jump forward. So you need to be drawing this. I'm just gonna try and make it look nice. Ella and Alicia are comparing scores on their college entrance exams. Ella's SAT score is 1,380, and Alicia's ACT score is 32. The mean SAT score is 1,000. So let's make this go over here about SAT. The mean is 1,000. The 0, 1, and 2, and 3 represents the number of standard deviations you are from the mean. With a standard deviation of 200. So this would become 1,200, 1,400, 1,600. And if I work my way left, I'd take away 200 from 1,000, take away 200 from 800, take away 200 from 600. Let's see here. Ella's SAT score is 1,380, which would lie somewhere around right here. All right. So I can tell that Ella is almost, but not quite, 2 standard deviations above the mean. Now let's look at Alicia's. The mean score on the ACT is a 21, standard deviation of 5. So if I do 21 plus 5, I get 26. And this is actually rounded data. It's actually 5.8 and 20.8, but whatever. 31 and 36. And if I take away 5, 21 minus 5 is 16, 11, and this poor mouth breather right here is 6. But anyways, Alicia, she made a 32. And a 32 is over here to the right of 2. So she is more than 2 standard deviations above the mean, above average. So who did better? This girl did, because she's more standard deviations above average. So Alicia has the better score. Now, the way this thing was labeled out was actually using what we call z-scores. You're probably not even going to write any of this down, but whatever. That's fine. This is the mean. This is the mean plus a z-score. And this is the mean plus 2 z-scores. So what is a z-score is the real question. A z-score, and I'll type this so you can read it better. A z-score is how many standard deviations something is above or below the mean. Sorry, I don't know why I wrote z-scores. How many standard deviations something is above or below the mean. That's all it is. It's just a conversion of a numerical data value into a standard deviation. And I guess I should write that down. It is a conversion of a data value into a standard deviation. Does it have a formula? Well, yes, it does. The formula is going to be x, which is our data value, minus x bar. So this is the data value. X bar, which is our mean. I know there's a couple of y'all who haven't figured that out yet. Over sigma of x, which is your standard deviation. Now, since z-scores tend to be decimals, we can either go old school with tables, which I'm not going to teach, but I remember them, or new school with calculators, as we cannot consult the 68, 95, 99, 7 rule. Here's our first example. The weight of captive adult female lowland gorillas is normally distributed with a mean mu of 82.3 kilograms and a standard deviation sigma 15.33 kilograms. Compute a z-score for Sasha. How can you use this score to find the percentage of captive adult female lowland gorillas whose weights are less than or equal to Sasha's? So again, let's go with our little formula. It's x minus x bar over sigma. So Sasha, right there, that's what I'm looking for, weighs 61.8 kilograms. we're taking away the mean, which they call mu here, 82.3, and we're putting over the standard deviation of 15.33. And we're just going to push some buttons and see what it is. 61.8 minus 82.3, pressing enter, divided by 15.33. Negative 1.34, that's what I'm going to round to. The z-score is about negative 1.34. Now, is that on my bell curve? Here's your bell curve. Negative 1.34 would be about right here. The answer to that is no. So I cannot refer to the 68, 95, 99, 7 rule like I did yesterday. So I get to use tech. And what we're going to do is we're going to press second vars. And if using z-scores, we have to establish something called an upper boundary and a lower boundary. So your lower boundary is going to be stuff to the left here, is left of what you're interested in. Now, since I'm curious about things that are less than Sasha, Sasha is the upper boundary. This is something that gets kids, and you always have to consult this. It's all about where an item lies on the curve and what you're interested in. Anyway, since I'm using z-scores, it's going to look a little bit funny here. Your mean mu is going to be 0, and your sigma is going to be 1. Standard deviation is going to be 1. Kind of refer to this version of the bell curve, which is meant for z-scores. And we don't actually always have to use z-scores. If they give us enough data, we don't have to. I'm going to go to second vars, normal cumulative density function. And this is kind of funny, but this is just what it is by default. Things less than Sasha, we're going to say, is negative 999,999 standard deviations beneath. Sasha represents the upper boundary because I'm interested in things that are below her, which was negative 1.34. Mu, the mean is 0. Standard deviation is 1. Paste. And there we go. 0.0901. So, lowland gorillas whose weights are less than or equal to Sasha's, there are roughly 0.0901 or 9.01% less than or equal to Sasha. So what is Sasha's percentile rank? She is the 9.01% rank. She's in the 9%. That's her percentile rank, 9.01, because percentile rank is the number of things that you are better than. Okay? So she's better than 9.01% of the population. That's her rank. And I know this is going to be new, and I know you don't have a calculator, and you're probably not playing along, even though I showed you where you could, but you're not going to do it. So here's another example. Scores from the spring 2023-2024 Algebra 2 benchmark were approximately normally distributed with a mean of 55.25% correct and a standard deviation of 15.34%. Jacob Hoy, who got beat by Nate Tarver, scored 86%. Compute a z-score for Jacob. All right, so we're going to take Jacob's score of 86. We're going to take away the mean of 55.25. We're going to put that over the standard deviation of 15.34. Now, if you take an old school stats class, they usually only round to the second or third decimal place. So if you're wondering why is Milbrath only rounding to 2 decimal places, because that's how they do it old school stats. Sometimes they go 3. But I get a z-score of about 2.004. Let's say 2.005 if I round. All right. Now, if I think about my table, this is going to lie somewhere about right here. Or not my table, my normal curve. What percentage of students scored perform better than Jacob? That's going to be over here. And it's going to be kind of funny. Your upper bound is going to be 999,999 standard deviations. And Jacob is the left boundary or the lower boundary. The lower boundary is Jacob. And Jacob is 2.005. So, and, you know, I already know some things, like it's going to be right around 2%. This is coming from knowledge of the bell curve, okay? Think about this guy, 34. We had, what, 13.5 in there. We had 2.35 in here. We had 0.15 in here. So I can tell you right now that it's going to be less than 2.5%. So I'm probably around 2.1, 2.2%. But it's just to the right of 2, so it's really, really close to that 2.5%. All right, we're going to go to second VARs again, normal cumulative density function. This time, Jacob represents the lower boundary, 2.005. And the upper boundary is going to be 6 nines. It's just something we do. That's 7 nines. Oops. Doesn't really matter. Just keep pressing 9. You'll get close enough. 0.225, according to my calculator. 0.225 as a decimal. I missed a decimal place. 0.0225, which is 2.25%. Now, what percentage scored worse? Well, if 2.25% scored better than 100 minus 2.25, and I'll show you another way of doing this, but 100 minus 2.25 has to be the answer, because 100%. So 97.75. Now, this is a skill that for some reason a lot of kids lack. It's called reasoning. Like, how did I know it was 100 minus 2.25? I just did. They're reasoning. But one thing I could do is I could approach this problem with the same methodology that I just did for Jacob. And I could actually just think about, okay, this is my upper, and all the way over here is my lower. So let's go back to second VAR's normal cumulative density function. This time the lower boundary is negative 99999, 6 nines, and the upper boundary is Jacob's z-score of 2.005. Then I go to paste. There it is, 0.9775, just like Milbrath told you. All right, now I'm going to do this next one a little bit different. I am going to compute the z-score, okay? I'm going to do that just because I want to go over the practice of z-scores. But if, and this is worth talking about, if the mean and standard deviation are given, I do not need to convert to a z-score. So I am going to compute this guy's z-score, but I don't actually need to. All right, so this kid scored 23% correct. The z-score is simply going to be 23 minus the mean of 55.25, sitting pretty over 15.34. That's how you do a z-score. Data value minus the mean over the standard deviation. So 23 minus 55.25, press that enter key, divided by 15.34 is negative 2.10. We're just going to go with that, negative 2.1. Let's go with negative 2.10. Two. So it's like right here. Like, he did bad. He did really, really, really bad. Poor thing. Now, no, I'm going to go back over here where I typed this out. You don't actually have to have a z-score to use normal CDF because it had an option there. So second VAR's normal cumulative density function. This guy, if I want to know who did worse than he did, this guy is the upper boundary, okay? And he made a 23. Oops, that needs to be the upper boundary. The lower boundary is just the negative 999,999. Now, the mean was given in the text, 55.25, and the standard deviation was given as 15.34. There you go, 0.0177 or 0.0178. I can't round today. I think I've got a head cold coming on. 0.0178 or 1.78% did worse. Okay? What percent did better? That would be 100 minus 1.78, which is going to be 98.22. This kid did bad. The percentile rank that this kid's mama is on Facebook bragging about is 1.78%. And mama thinks that's outstanding. She is so happy and proud of her little angel. He's kind of dumb, mama. Like, he's really kind of dumb. You don't brag on that kid. You don't. Because you and I both know you're still telling him to brush his teeth every single day before he leaves school and every single night before he goes to bed. Because he's special. He's not smart. Facebook mamas. Moving forward. Student has an ACT score that is 1.67 standard deviations above the mean. Notice I did not give data values. So when only a z-score is present, you need to remember that your mean, mu, is 0, and your standard deviation is 1. All right, what percent of kids did worse? So this kid is 1.67 standard deviations above, and I want to know who did worse. This kid is the upper boundary. This is the hard thing that kids struggle with understanding, is which one's upper and which one's lower, and you have to visualize it. You know, I've got a nice chart here every time thinking about that. You have to draw the curve and you have to visualize the curve. That's the big thing. Visualize the curve. Visualize it. Visualize where they lie on that curve. So we'll go through normal vars or normal CDF, second vars, normal cumulative density function. And if I want to know who did worse, the kid is the upper boundary. So 1.6, sorry. I keep thinking for some reason you typed that in first. The lower boundary is going to be your -6/9. Your upper boundary is 1.67. Since I'm using z-scores, the mean, mu, is 0, and the standard deviation is 1. And I hit the paste key. Most of the population did worse than he did, 0.9525, or 95.25% did worse. What students did better? Now, hopefully you catch on that this is 100 minus 95.25, which is going to be 4.75%. Hopefully you catch on to that. What is the student's percentile rank? The truth is, we'd round, we'd say 95th percentile. This is the kid that you brag on. You brag on this kid. This is the one you brag on. Out of 100 people, they're better than 95 of them, okay? That's the kid you brag on. Plain and simple. Brag on that kid. They deserve it, not the other one. The other one's dumb. Anyways, there's your z-score lesson. Hopefully this made some sense to you. Otherwise, you are probably this kid. Don't be that kid. Don't be him.